In section 2.3, we're going to take a look at an important property of functions called inverse functions. And so first, to kind of define what we're talking about with these inverse functions, we're basically asking for a function that undoes something that has been done. This is your Control-Z function. And to kind of introduce this visually, what we're talking about is we've already talked about a function machine, f of x. And what we're suggesting in this video is for every function machine, there is another machine that's very closely related to it that we're going to call the inverse function machine. And the way we notate the inverse function is really similar to the regular function. We're just going to put a little -1 up above. That's not very clean. Let's try that again. A little -1 up above in between the f and the x. And that's not an exponent. I know it looks like an exponent. We do that just to make it confusing. When we see that f to the -1x, we read that as the inverse of f of x. This is the function that undoes what the f of x function does. In other words, if we were to take the number 5 and throw it into the regular function machine, it'll come out different, maybe a -2. The idea is if we take this -2 and plug it into the inverse function, it's going to spit out what we started with, a 5. Maybe a more general way is we're going to plug in an x to the function, we get a y out. The inverse takes the y as an input, and it spits the x out as an output. It takes you back to where you started. And you might notice this setup is really similar to how I visually depicted a composition of functions. In fact, the concepts are related because if we want to check if functions are inverses, the way we do that is we compose the functions. And when we do that, it should equal x. And the reason for that is what we just did here a second ago in this example. When we plugged x in, we got y, and then when we compose it, we get back to x. The composition will equal x if the functions are indeed inverses. So for example, if we had f of x equals the square root of x plus 5, and g of x, another function, the opposite of square root is to square something, the opposite of adding 5 is to subtract 5, so we might assume that the inverse function is x squared minus 5. The way we verify this is we find the composition f of g of x. Well, g of x, that inside stuff, is x squared minus 5. And so when we plug that in for the x in f, we get the square root of x squared minus 5 plus 5. And then we start simplifying. -5 plus 5 is 0, so we have the square root of x squared. And the square root of x squared is simply just x. We have, in fact, shown that these functions are inverses if we limit the domain, but we'll talk more about domain later in the video. Let's do one more example where we check to see if two functions are inverses. Let's say f of x equals 2x minus 3. G of x, then, we would assume we're going to do much the opposite. So instead of multiplying by 2, we'll probably divide by 2. And instead of subtracting 3, we'll probably add 3. So it would make sense to say that we have inverses. The last example, we showed that yes, they were inverses. Because we did a composition, and the composition equals x. So let's see if the composition equals x here. We'll take f of g of x. Well, that means we stick g of x inside the f function, which is x over 2 plus 3. And if we plug that x over 2 plus 3 in for the x, we have 2 times x over 2 plus 3 minus 3. And then we can start simplifying. We'll distribute the 2 through, and when the 2 goes on the fraction x over 2, we're just left with x. And 2 times 3 is 6 minus 3. What you notice this time is we end up with, if I could change colors, whoops, too far, x plus 6 minus 3. When we combine like terms, we get x plus 3, not x. These are not inverses. For them to be inverses, their composition would need to equal x, and this one equals x plus 3, so that does not work. So if it doesn't work, how are we going to actually find the inverse? The way that we find an inverse goes back to this picture. Notice for the inverse function, instead of x going in, we have y going in. We've almost swapped the roles of x and y with the inverse function. Now y is the input, and x is the output. So that's what we're going to do to find the inverse, is we're going to swap x and y. And y, remember, is what's really being represented with the f of x, the function notation. So if we've got an equation such as f of x equals x minus 3 to the 5th plus 2, we'll think about that f of x as a y, and then we will swap the x's and y's. So instead of y equals, it's now x equals. And instead of x minus 3, it's now y minus 3 to the 5th plus 2. Generally, equations are solved for y, so we're going to do that here as well. We're going to solve our function for y. And we do that by subtracting 2 from both sides. X minus 2 equals y minus 3 to the 5th. Get rid of the 5th power with the 5th root of both sides. 5th root of x minus 2 equals y minus 3. And finally get the y alone by adding 3 to both sides. And we get 3 plus the 5th root of x minus 2 equals y. Or since it's alone, we'll say now that is our f inverse function. So to find the inverse function, we simply swap our x and our y values. It works with equations of all types, but it also works with graphs. Let's take a look at this graph here. Let's put a point on the graph here at negative 2, 3. We'll do a point on the graph here at 1 or 0, 1. And we'll do a point on the graph here at 2, negative 1. And I'm going to connect them with a loop and a loop. Now, if we wanted to graph the inverse of this function, the inverse is going to do much the opposite thing. The x's and y's are going to switch, which means this first point, negative 2, 3, is going to switch orders to now being 3, negative 2. So I'll put a new point at 3, negative 2, which represents that xy being switched. Similarly, the 0, 1 is going to flip to now be 1, 0. Similarly, the 2, negative 1 is going to flip to become negative 1, 2. And now when we connect the dots in much the same shape, but this time switching directions, we end up with this looking inverse, if my green dot doesn't disappear. Notice the shape is exactly the same where it leveled out flat. Now it leveled out going up. It's kind of flipped all those x's and y's around, giving us our new graph. Well, there's a little problem with this method, though, that we've kind of avoided up till this point. And that is if we want to make the inverse a function. First, a definition. A one-to-one function has one input for each output. And this is similar to our definition of a function. A function had one output for each input. This one-to-one function is the opposite. One-to-one function is going to pass not the vertical line test, but the horizontal line test. The idea is the inverse is going to tilt it on its side and turn it backwards. When it's tilted on its side, is it going to still pass the vertical line test or the horizontal line test before it was flipped? So here's a problem that's not one-to-one. This is a problem. Let's consider a graph like x squared plus x minus 2. If we were to graph this guy, a rough sketch of what it would look like would be something like this. There's a point over here at negative 2, 0. There's a point over here at 1, 0. And there's a point down here at the bottom that's negative 1/2, negative 9/2. And if I were to try and graph the inverse function, negative 2, 0 would flip around to be 0, negative 2. And 1, 0 would flip around to be 0, 1. And negative 1/2, negative 9/2 would flip around to be negative 9/2, negative 1/2. Notice this is not a function because it does not pass the vertical line test, which goes through the function in more than one spot. And that's not allowed. That's because this blue function was not a one-to-one function, because if I were to draw a horizontal line, we've got the same problem. A horizontal line goes through it in more than one place. And so what we're going to do to fix this problem is we're going to eliminate the inconvenient part of the graph. What we're going to do for our solution is we are going to limit domain so it is one-to-one. In other words, if I look at my function, there's a left side and a right side to this blue graph. If we were to get rid of one side, and it doesn't matter which, let's say I cross off the left side, now you see that it is one-to-one, because that's going to turn into the bottom of the function, and if I get rid of the bottom of the function, just the top is there, and now it does pass the vertical line test. Now it is a function. So we limit the domain of the original problem. How about we do it with inequality symbols? That'll be good enough. We're going to say x has to be greater than or equal to that starting x value of negative 1/2. And if we restrict the domain, we've gotten rid of that extra arm that violated the vertical line test in the inverse or the horizontal line test of the original problem. We want to make the original problem such that a horizontal line is only going to cross at one point. Now that does provide choices, though. Sometimes there's more than one, oftentimes more than two, choices as to how we restrict the domain. For instance, look at this graph. Let's say this point over here on the left is -2, 0. This point at the first top is -1, 3. Point down here at the bottom is 1, -2, and we've also got 3, 0. And I guess you also noticed it went through the origin, so we'll call that one 2, 0, 0. Choices in how we restrict the domain. You notice if we were to draw a horizontal line, it's going to cross in 1, 2, 3 places. It's not going to pass the vertical line test when we make it into an inverse. So what we're going to do is we're going to restrict the domain so that it only crosses in one place. The catch is there's several options for this. One option is if we just look at the left part of the graph, the yellow. That would pass the vertical line test if we flipped it over. So doing that, we're limiting the domain to x is less than, because we want the left half. The x value there is -1. And so if we just look at x less than -1, we've got a point at -1, 3, which flips around to become 3, -1. Let's make it green. 3, -1. And the -2, 0 is on this line, which flips around to become 0, -2. And the graph becomes this guy. This lower part is the inverse of our function. But we didn't have to cut it there. We could have cut it and said, gee, we want the middle part of the graph, because that'll also pass the horizontal line test. If we do the middle graph, we're saying x is between our two x values of -1 and 1. Staying between those x values of -1 and 1, we end up with the edges at -1, 3, which when flipped becomes 3, -1, 0, 0, and 1, -2, which when flipped becomes -2, 1. And then if I connect these dots, we get this little guy, which is a function. Of course, we could have cut it and just kept the right side. If we do just the right side, we're saying x is bigger than that x value of 1, and we can graph that inverse. So the first part, the endpoint, it starts at 1, -2, which when flipped is -2, 1. Goes to 3, 0, which when flipped is 0, 3. And then it goes up forever from there. So this graph that we started with, which was really wavy, had 3 options for how we can slice it in order to determine the inverse. As long as the inverse is still a function passing the vertical line test, it still will pass for our final solution. So there's 3 answers for this problem. Other problems are maybe more than 3. Some of these are, there's no set one answer, as long as your answer passes the vertical line test. So let's combine this idea of one-to-one and restricting the domain with actually finding inverse functions. So this is going to be letter D. First we're going to look, is it one-to-one? And then we're going to find the inverse function. And if it's not 1 to 1, to find the inverse, we may have to restrict the domain. So our first problem we're going to look at is f of x equals x plus 4 over x minus 3. And to help us out to determine if this is a 1-to-1 function, we're going to have our calculator do the graphing for us. In our next unit, we're going to look at how we can actually graph this without a calculator. But for now, we're going to use our calculator to help us. And if you hit the y equals button on your calculator, it'll take you to a place where you can type in your functions. Now with fractions, we're going to need to put parentheses around the numerator and denominator so the calculator knows the entire x plus 4 goes in the numerator, close the parentheses, divided by x minus 3, close the parentheses, and if we hit enter, we've now got that function listed in the y1 equals. The way we graph this function is we hit the graph button in the top right corner above the arrow keys. And the graph will slowly draw a picture for us. And what I want to notice is if we were to draw a horizontal line through this graph, it would only cross the graph at one place. Since this does in fact pass the horizontal line test, it is 1-to-1, and we can go ahead and find its inverse the way it is. Now it's possible your graph has a vertical line through at the point 3, at x equals 3, a vertical line. If there is a straight up and down vertical line, what that actually is that's a vertical asymptote. You can actually get rid of that vertical asymptote if you hit into the mode and scroll. There's a lot of options here in mode. Scroll down from connected and scroll over to dot, and that'll get rid of any asymptotes you might have. It'll make the graph a little more pixelated, but it gets rid of that asymptote. I like to keep connected on. Some calculators recognize it's an asymptote and some don't, so some may draw that vertical line in and some may not. But just know if you see a vertical line, that's probably an asymptote. That's not actually part of the graph. Okay, what's important though is we know it is a 1-to-1 function. We can just make it the f of x into a y and then switch the x's and y's around. So we've got x equals y plus 4 over y minus 3, and then begin solving for y. Clear the fraction by multiplying by the common denominator of y minus 3. We have y's on both sides, but we saw this in our previous unit. We know we need to multiply everything out and get the y's onto one side, everything else on another side. So I'm going to distribute the x. So we have xy minus 3x equals y plus 4. Let's move the y's to the left. We'll subtract y from both sides and move everything without a y, the 3x, to the other side by adding 3x. Be careful about like terms. We've got xy minus y equals 4 plus 3x. Those aren't like terms, so we can't combine them. But what we can do is factor a y out of the left side, leaving behind x minus 1 equals 4 plus 3x. Get the y alone by dividing out the x minus 1. And y is alone. We now know what f inverse of x is. It is going to be the 4 plus 3x over x minus 1. So it is 1-to-1, yes. And we found the inverse function. No need to restrict the domain because it was 1-to-1. Let's try one last example. let's consider f of x equals x to the fourth minus 1. We're going to bring our calculator back, hit the y equals button. It should default to highlighting that first equation, and if you hit the clear button right underneath the arrow, it'll delete out that old function. And now we can type in x to the fourth power. We get an exponent by going right above the divide sign. Fourth power. In some calculators it'll stick you in an exponent, in other calculators it'll actually draw the little caret symbol. If you are actually physically up in the exponent, you need to scroll over to get out of the exponent. Minus 1, and then we hit graph. And there is our function. Almost could sketch copy of it here. What our function did was it came down and bent and came back up. And the important thing here is to notice it does not pass that horizontal line test. We are going to have to restrict our domain. It doesn't matter which side we restrict, we just need to get rid of part of it, so I'm just going to get rid of the left side. Which means I'm basically interested in when x is greater than or equal to, what's our x value down there in the center? X is greater than or equal to 0. So that restricts the domain. Now we're ready to find our inverse. Remember, f of x is really y. So if we switch x and y, we get x equals y to the fourth minus 1. Add 1 to both sides. And x plus 1 equals y to the fourth. Get rid of fourth power with a fourth root. And because we are only interested in the right side, we're only interested in the positives, we don't have to worry about plus or minus. We just went to the right side. So y is equal to the fourth root of x plus 1, or we could say f inverse of x is the fourth root of x plus 1. We now have our inverse. So that's what we're looking at today, finding inverse functions by swapping x and y, whether that's in the function or that's on the graph. We're also looking to check if things are inverses, and the way we check them is we compose the two functions together. The only thing to be careful of as we begin finding these inverses is if we don't pass the horizontal line test, we have to restrict our domain, cut off part of the graph, so that when we find the inverse, it will still be a function. Take a look at the homework, practice, 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 and we will see you in class.